Good morning, good afternoon, and good evening, everyone. So today we're going to be talking about gradient descent. We're basically going to do a brief review of it. Um, so yeah, let's just hop right into it. So if we want to solve our linear system ax equals b, well, we can use different kinds of methods, right? So we can actually use direct methods, or we have seen direct methods being used, such as, I don't know, Gaussian elimination. We've seen that. We've also seen LU decomposition. We've also seen iterative methods, right? Which is what we talked about in our previous scientific computing video. And these iterative methods, again, were derived from, well, from a system of linear equations, right? Okay. So it's this system. Let's be general about it. A11x1, uh, A12x2, all the way to A1 and xn equals B1. 2, 1, 2, 2, 2, x2, 2n, xn, B2. And this goes all the way to n. Xn. Okay, so this is an n by n matrix. N2, xn, and n, xn. Okay, so that's our linear equations. I just wrote it out. Now we want to consider it from an ax equals b standpoint, right? So here's the new lesson actually. So here's our observation. If we consider it from an ax equals b standpoint, let's make some assumptions. Let's assume ax equals b. Ax and b are all real numbers, right? So no matrices, just numbers. And let's use functions here. So we let f of x be ax squared over 2 minus bx. And so this is a quadratic function because it's a polynomial of degree 2. And so we do some cases. Well, if our a is greater than 0, well, we have a concave up parabola with its minimum at b over a. And if we have a great less than 0, so meaning it's a negative, well, now we have a concave down function. And its vertex is b over a. And if, let's say, the minimum, so these are called the minimum and the maximum. Here in this case, it's a given. When x is at b over a, well, mathematically, we know that, okay, so so here's the math, right? We go to calculus. When we take the derivative and we take the root of that, so we do f prime. When we take the root of a derivative, okay, what's the derivative? Well, this is just ax minus b, and we set it equal to 0, then we can find ax equals b, which is what we got earlier. So what does that mean? So apparently some derivative calculus is in play here, and it somehow connects us back to what we initially have, which is ax equals b. Now, what if instead of finding ax equals b directly, so using direct methods, or through a system of equations using iterative schemes, well, what if we find it using the minima of a function, right? So here's the new technique. So what if we find the solution of ax equals b by finding minima of function? Minima or maxima, doesn't really, maybe a function that's like ax. Let me rewrite it. A over 2x squared minus bx. Maybe something like that. Something like a quadratic function. Right? So let's do it. Let's do it in our ax equals b linear system. Here we say our A is a matrix of, it's a square matrix, n by n. That means our B is just n by 1. Then we have this function here. And I'm assuming it's a quadratic. Okay, x transpose ax minus b transpose x. And here, my x is a vector from x1, x2, all the way to xn. Right? Okay. We're going to consider that function. Right? And then what happens? Instead of the derivative of f, well, we now have multiple variables to consider, right? And so we look at the gradient. That's what we do. How do we know we have multiple variables? There we go. We have x1, x2, x3, x4, all the way to xn. And we have to take the derivative of each of them, right? So we have multiple variables to consider. So we find not the derivative, but we find this thing that we call the gradient, right? So let me go ahead and do that. So my gradient, the gradient of my function, well, here we just take partial derivatives of each of them with respect to each variable that we have. And now I can confidently say from here that I can understand this to a better level than previously when I discussed this, because I haven't looked at partial derivatives. But here we're getting each, and I mean each variable, and with respect to that variable. We're getting the gradient of the function with respect to each variable. So we'll have like what? Multiple derivatives, multiple slopes at particular points. So yeah, that's gonna be the idea, right? So here we're just talking about ideas. We're not going into concrete stuff yet. So if we look at a 1D derivative, well, it's just the instantaneous change of a function. But if we look at an ND gradient, we don't know how many dimensions it is. So if you look at an ND gradient, well, this is just basically looking at each element, and each of that element shows instantaneous change. Right? So it's not just a single element, unlike the previous Calculus 1 course. So it shows each element's instantaneous change of that particular function. A function that contains, well, actually, no, that's it. That contains tons of variables, right? Wait, there must be a meaning to this note because it's like W. I'm just trying to Google it up. I don't know what it means. Okay, never mind. Okay, and here another fact that we might want to consider is that the vector is also the direction of the steepest descent. So when our vector is pointing towards something, that's where the direction of the steepest descent is. Okay. So we say that when we have a function that looks like this, what's its gradient? Well, the gradient of that particular function is just 1/2 a d x plus 1/2 ax minus b, right? And we're saying that if my gradient is 0, so here I'm gonna say if my gradient is 0, then my 1/2, then here I can factor out my x, as well as my 1/2. I can factor both of them out. Well, this is just equal to b. And if it's symmetric, meaning A transpose is the same as A, then we'll get the solution. So I'm gonna say when A, or A matrix, is symmetric, meaning my transpose is just equal to itself, the original matrix, I mean, then we would get the solution, right? So we would say B is 1/2 of A transpose plus AX. Well, this is just equal to what? AX, right? And so that solves the thing. And so that's the idea of our f of x. We can either have a minimum or a maximum, right? So here we say that, okay, let's introduce something here. We're going to say that A is a positive definite. Let me go into that first. And what does it mean if it's positive definite? Well, my function has a minimum. That's what it means. And we're going to define the mathematical definition. We're going to say A is positive definite if we fulfill these conditions. We're going to say that our x transpose AX is greater than or equal to 0. Then it would be a positive definite. Here we're saying x is a vector. Okay, so examples of symmetric positive definites. Let's look at that. Actually, let me just look at that symbol real quick. Not maybe it rings a bell when I do this. Okay. Yeah, not super sure. But I should be fine. Okay. Let's look at some examples of these. We're gonna look at symmetric ones. Okay. Symmetric, positive, definite. SPD. Okay, we actually have one example here. So we let A be a matrix of n by m dimensions. Okay? And so that means its transpose times itself is symmetric, positive, definite. Right? And so we say that A, its transpose times itself, when we get to the power of t, well, here we get AT or transpose we get this. If we transpose it, then transpose it again, we just get itself, right? What else? Okay, we have x, or vector x, we take its transpose. My matrix A, we take its transpose times ax. Well, this should just be the transpose of my A times x multiplied by A times x. And this should give me a vector that contains those two. Then, I don't know, we can switch a placeholder here. I said that ax is equal to c. And then from there, I do a summation that goes to m. And then j starts at 1. So here we start at cj squared. Now, how do we find the minimum of our function? Well, the gradient of our function was the direction of steepest ascent. So how do we descend? Well, we just change its orientation, right? So again, how do we find the minimum of my function here? I taken an x, right? Okay. Well, this is 1/2 x to the t a x minus transpose of my b x. So what happens here? Well, we're going to say that this was the direction of steepest ascent. Ascent meaning going up. And so to change it, well, we just have to change its orientation. Now this is direction of steepest descent. And therefore, we can make an original guess x naught, and we can use our iterative scheme. So we can do that. So we say xj plus 1, which is the next value, which is just xj minus tau gradient of f of xj. Right? Here we say that my gradient is just axj minus b. And so again, this is just using gradient descent and iterative schemes. So where t or tau is the step size. This is the method of steepest descent or gradient. And this can be fixed for all iterations. And can also verify or vary. It can also vary based on the iteration, which leads to other iteration schemes. So that's just something I'll leave it up to you guys to discover. But the idea being, we talked about 3 ways to solve for AX equals B, mainly direction methods, iterative methods, and this idea of gradient. And here we talked about gradient descent pretty much. Anyways, yeah. I hope you guys enjoyed this video and I hope you guys learned a lot. And I'll see you all in the next one.